All right, guys, let's go ahead and go over the warm-up question that is on my screen. It should also match the one in MyOpenMath in that warm-up assignment. So if you haven't yet answered it in there, you need to make your way there so that you can type in your responses as we are going over it. The question says, describe the motion of the object shown, including its average speed, any changes in direction, total distance, and total displacement. And so you had to kind of do what we've been doing for the past couple of days and be able to read this position time graph. So the average speed, okay, the first thing we're going to answer, average speed. In order to calculate average speed, and we talked about this yesterday, it's total distance divided by total time. The total time on the graph is real easy to see because it just shows you 6 seconds. You can just look at the x-axis. The total distance, though, you do need to take a look at each little segment here and how far the object traveled during that segment and add them all together regardless of their direction because distance is a scalar quantity. So the first portion here, the object traveled from a position of 1 meter to 2 meters, so that's 1 meter. Then it's at rest. Then it travels from 2 to 4, so that's 2 more meters, so now we're at a total of 3. And then it goes backward 1, which means we're at a total of 4 meters. We don't care about the backwards, we're just going to add all the pieces together. So that means it traveled 4 meters over the course of 6 seconds, and so you would do 4 divided by 6, which is 2/3, or 0.67 if you round that, meters per second. Okay, the second question asks you to describe any changes in its direction. Okay, does this object change direction? Let's start there first. Yes, it does, because it goes from having a positive slope to a negative slope. That's where it changes direction. It only happens once, right here, at a time of 5 seconds. Now, at a time of 1 second, it stops, but it doesn't change direction there. It just stops briefly before moving again. So the only change in direction is at a time of 5 seconds. The total distance, we actually found that in order to answer the first question to be 4 meters. The total displacement, on the other hand, all you have to do for displacement is look at how far you are from where you started. I started at 1 meter. My final position is 3 meters. And so if I wanted to know what my displacement was, I would take my final position 3 minus my initial position 1, and I am 2 meters away from where I started. It's technically positive 2. Okay, and so my total displacement is 2. So go ahead and submit those, and if you do, it should give you full credit for the warm-up for today. We are going to pick up with some notes on speed and velocity to elaborate a little bit further, add in some graphs, add in some calculations, and that should help you to feel better prepared to answer all of the questions in the homework assignment 103.3 Speed and Velocity Problem Set. Some of you may have started it yesterday, but again, you may not have known how to do all of it. That's okay, because we hadn't finished talking about our notes. The other thing I just want to give you a heads up about is that on Monday, you're going to have a quiz, basically, in class, a CFU. It's also in MyOpenMath, but a CFU, whenever I put that in MyOpenMath, you don't get partial credit whenever you go back to answer it a second time. Right now, if you miss it, you can answer it again and you get partial credit, but on Monday, that won't be the case. It's basically like a quiz. Okay, so let's go ahead and get through our notes so that we feel better prepared for both of these two upcoming assignments. One of them due tonight, 103.3. Okay, so let's first go ahead and go back to our graphs. We have already talked about position time graphs, but today I'm going to introduce you to another type of graph called a velocity time graph. And so we're going to show what different types of motion look like on these different types of graphs, starting with what does an object look like when it's not moving? If we have an object at rest, what does that look like? We already know what it looks like on an XT graph. Hopefully you remember. That's if you have a horizontal line. And it doesn't have to be right there. It could be anywhere. If you have any horizontal line on your XT graph, whether it's above 0, at 0, or below 0, that means the object is at rest at whatever that position is. Okay, and so if you see a horizontal line, we're at rest. On a velocity time graph, if I want to show that I'm at rest, that means I can't be moving. It means my velocity has to be 0. In order for me to have 0 velocity plotted on a velocity time graph, I have to have a horizontal line, but it has to be at 0. Okay, so on my VT graph, yes, it's a horizontal line, but it has to be on my x-axis where my velocity is 0. On my position time graph, it can be anywhere because this is simply showing my position doesn't change. Wherever I started is where I still am. Okay, so again, if you want to show an object that is not moving or at rest on your xt graph, that's going to be a horizontal line with a slope of 0, and it can have any y-intercept. On a VT graph, that's going to be a horizontal line on the x-axis. Okay, so again, we're just jotting down how these different types of motion will appear on these different types of graphs. So an object at rest, you should be able to identify it based on either the xt or the VT graph for that object. I am going to be moving through these possibly faster than you're copying them down, depending on how quickly you're writing. So if you want to open this up on your own screen so that if I do happen to go a little faster than you, you can still copy it. I am currently on slide 128. Okay, and you can open it up there on your own screen because I'm going to go ahead and move on to the next slide. If I want to show constant forward motion, then on my xt graph, I need to have a line with a positive slope. Straight line, positive slope. Again, doesn't have to start at 0, could start anywhere, but I need to have a positive non-zero slope. On my VT graph, if I want to show constant forward motion, okay, velocity is a vector, so it has direction. And the way that I know that I'm moving forward when I look at my velocity is if it's a positive number. So if I want to show constant forward motion, I'm going to have a horizontal line in the positive region of my graph where my y values are positive. So somewhere up here. It doesn't have to be right here. It could be higher. It could be closer to this 0, but it needs to be above the 0 for it to be a positive number. And it needs to be a horizontal line for it to be a constant velocity. So pretend there are numbers here. Maybe this is a constant velocity of positive 2. So it's positive 2 meters per second the whole time. That's how that would look on a VT graph. And if it were positive 2, okay, then the slope of this line would have to be positive 2 as well. We talked about, if they're showing the same motion, rather. We talked about how the slope on our xt graph tells us our velocity, how fast we are going. Okay, so you can match the two up even, or more carefully actually, if you have numbers on it. All right, so constant forward motion, xt graph, positive non-zero slope, VT graph, horizontal line in the positive region of the graph where you have positive y values. Constant backward motion on my xt graph, I'm going to have a negative straight line slope, so a negative non-zero slope. And on my VT graph, I'm going to have a horizontal line again, but this time to show that I have a backward velocity, it's going to be down here in the negative region of my graph. So again, pretend there are numbers. Maybe this is negative 5. I don't know. I don't have it numbered. But that would mean that my velocity was 5 meters per second in the negative direction. Okay, so negative part of the graph, horizontal line, that is how you're going to represent constant backward motion on a VT graph. And again, these two graphs could show the same motion. Again, if that were the case, then the slope of my xt graph, let's say it's negative 5, if I find the slope here to be negative 5, then this had better be at negative 5. You can match them up to each other, and you will be asked to do that, to say, which of these graphs matches, which of these VT graphs matches this xt graph. Okay, so you should be able to go between the two, and we'll have time to practice that more a little bit later. All right, so we know how to show something at rest. We know how to show something moving with a constant forward motion and with a constant backward motion. And of course, we've seen plenty of graphs where you have different segments of the motion where it moves and it stops and it moves and it goes back, like in the warm-up. Okay, so each of those pieces, you can see what that would look like here, and you can see how you might graph that same thing on a VT graph. Okay, so let's take an example that we looked at already. So this is the one from yesterday about Admir riding his bike. Okay, and so again, just to remind you of this scenario, he rides his bike 10 miles east, it takes him an hour, then he rides 12 miles west, it takes him 1.5 hours, and we graphed this yesterday. Okay, so we already know what the position time graph looks like. We can also figure out what the velocity time graph would look like for this same motion, which is what we're going to do. This is what I would expect my velocity time graph to look like for the same motion. Because for the first hour, he's traveling 10 miles per hour, 10 miles in 1 hour. Okay, and so I have a horizontal line for a constant velocity at 10 miles per hour. Then, for the next 1.5 hours, he travels 12 miles, and we found that the other day to be 8 miles per hour. And so I have this at -8 because it's in the backward direction, but 8 miles per hour in the negative direction down here for the next 1.5 hours. And in between the two is the moment where he changes his velocity from +10 to -8 somehow instantaneously. I'm just going to tell you right now that's not actually possible to do. You have to actually slow down first and then speed up again in the other direction. But as of right now, we are simplifying everything because we haven't talked about acceleration yet, and that's really what you would have to include in order for it to look correct. Okay, and so we're not worried about that, but you can see that it goes from +10 to -8. Okay, and this matches the slopes that I had on this graph. This is a slope. Okay, if you look at rise over run, rise 10, run down here 1, 10 over 1 is 10. This is at 10. If you look at the slope of the other line here, we go from 10 down to -2. That's a change of -12. And that takes place over a run. If I look at my change in x of 1.5, -12 divided by 1.5 is -8. Okay, so we're just matching it up. All right, so this is what that same motion would look like if we plotted it on a VT graph. So you need to be able to go from one to the other, just like this. All right, and I just mentioned this, but if you find the slope of your xt graph, we talked about how that tells us velocity, and you can see why. Look at the equation. Velocity is displacement over time. Slope is rise over run. And on my graph, my rise, my change in y, is my displacement. It's my change in position. And my x is my time, okay, on my x-axis. And so I would have change in position over time or displacement over time. That's what the slope would be telling me. So the slope on my xt graph tells me my velocity. If I find this slope, I know where to plot this. Okay, so if this is -8, this is -8. Okay, so if we take a look at this, how can you tell if someone is traveling backwards? Again, we already talked about this. On my xt graph, I have backward motion if I have a negative slope. Okay, we just wrote it down in the notes a second ago too, but I have backward motion with a negative slope. On my VT graph, I don't have any slopes. Everything's 0, okay, because we're talking about constant motion right now. So the way that you tell backward motion here is if it is in the negative region of the graph. So if I have a negative velocity, then I'm going to be moving backwards. Okay, so again, be able to answer questions like this. You know, when am I moving backwards? You could say from 1 to 1.5 hours. Looking at either graph, you should be able to tell me that. Or sorry, 1 to 2.5. Okay, how can I see how fast someone is moving? On an xt graph, I have to find the slope, okay, because my change in position over time is velocity. That'll tell me how fast. On my VT graph, it's really easy. I just read the value. Okay, this line, this horizontal line is at +10. Therefore, I'm moving +10 because that's what this axis is measuring, is velocity. So read what the point is, where your data point is at that point in time. That will tell you how fast you're going at that point in time. You can find your instantaneous velocity. That's your velocity at a certain instant. So if I said, how fast are they going at 1.5 hours? I would look over here, 1.5 hours, oh, they're going -8 meters per second, or sorry, miles per hour. Okay, if I look over here at 1.5 hours, I would be along this straight line segment, and I just have to find the slope of the segment that contains the point. Okay, it's a lot easier on a VT graph to answer this question because I don't have to do any math, I just have to read it. How can you see how far someone has traveled? Well, that's a lot easier to do on an xt graph because if I look at it, I have my positions marked. I go from 0 to 10. I traveled 10 miles. Over here, it's a little bit trickier. To answer the question how far someone travels when you're looking at a VT graph, you actually have to do some math. Okay? In fact, you have to find this area. Find the area between your data points and the x-axis. We call it area under the curve, but it's between the line and your x-axis. Okay, and the reason you're doing that, think about it mathematically. This is a rectangle, right? Area of a rectangle is length times width. We all agree with that. Okay, look at the length and the width of this rectangle. Velocity and time. Velocity times time is the equation for displacement. We know that velocity, if I write it on the board, velocity is displacement over time, right? Velocity is displacement over time. If I rearrange this equation and I multiply both sides by time, then I get displacement is velocity times time. That's length times width on my graph. That's velocity times time. So if you find the area, it will tell you how far you have gone. Okay, or you just read it. I traveled 10 miles per hour for 1 hour. How far did I go? 10 miles. That's what you're going to get if you multiply length times width and find the area for the first segment. Okay, so you can answer that question with a VT graph as well, but you have to find the area. And that's what this says. Anytime you look at an equation and you're multiplying your x-axis times your y-axis, like velocity times time is displacement, here's that equation I just showed you. Anytime you're doing that, find area, because that's what you're doing. You're multiplying your x times your y, you're finding the area of a rectangle. Okay, and so that'll give you, in this case, displacement. So you can figure out the area of this should match your change in position over here. So again, that's a rule that, by the way, this find slope, find area thing that I have on my screen right now works with every graph that we do in this class. So if you look at a graph and you look at the variables on it, and then you look at your equation sheet and you're like, oh, this graph has force and time, and I have an equation here that says J equals F times T, which will be an equation later on. Then you can say, okay, I guess I can multiply F times T. I can find the area and get J. Okay, so you can do it with any graph. So that's a rule you're going to see over and over throughout the course of the year. All right, these are some questions. They're actually from, I think they're still on your unit summary. They were on an older one, but I think they're on this one. So let's go ahead and see if we can answer some questions from this VT graph. So we have a velocity time graph showing the motion of two people named Art and Polly. So I'm guessing they're in a nursing home, because I don't know anybody named Art or Polly. But let's go ahead and go with it. Okay, so the first question says, describe Polly's motion. What is Polly doing? Let's see. I hear some whispers, but nobody's quite loud enough. Avery, were you one of them?
Oh,
what do you think?
She's at rest.
You think she's at rest. Okay, why do you think she's at rest?
Because it's a straight line.
It is a horizontal line. What type of graph is it?
Oh.
It's a very easy mistake to make. We have two different types of graphs now, so be careful. This is a velocity time graph. So let me ask you again, now that we know that, what is Polly doing?
She's constantly going forward.
Yeah, she's constantly moving forward at 1 meter per second. That's what this velocity time graph says. Polly has a constant velocity. Okay, who's traveling faster at the start of the graph? Okay, so take a look at the graph. Who is traveling faster at the start of it? What do you think, Will?
Polly.
Polly. How fast is Art traveling at the start?
He's not.
He's not. He starts from rest. Okay, so Polly's traveling faster. How do we know? We just look at the y-intercept. Okay, what happens at 2 seconds? Okay, or thereabouts. What do you think is happening at 2 seconds? Anybody want to volunteer an answer for that one?
Art passes Polly.
Okay. Garrett said Art passes Polly. Okay, which would be true if this was a position time graph, because that would mean they were at the same place at the same time. But this says they have the same, what? Velocity. That's the point at which they're traveling the same speed. They're not in the same place, okay, because Art wasn't going the same speed the whole time. We haven't talked about this yet, but what is Art doing?
Accelerating.
He's accelerating, he's speeding up. That's really our next unit. But I just wanted you to see what that might look like on a graph. Okay, but at 2 seconds, they're traveling the same speed. They haven't passed each other yet, just the same speed. Okay, who is traveling slower at 3 seconds?
Ollie.
Yep, Polly's traveling slower. Was that you, Mason? Thank you, sir. Okay, at 3 seconds, Polly's traveling slower. And again, all you have to do is read the Y value at 3 seconds. Art's going about 1.5, Polly's going 1. Okay, at 2 seconds, who has traveled farther? It's maybe a little bit of a trickier one. But who's traveled farther at 2 seconds?
They traveled the same. Equal.
They're not the same. If somebody's traveling 1 meter per second, okay, the whole time, and somebody else, it takes them 2 seconds to get up to that speed, they won't have traveled as far, will they? Okay, because they started out at rest, so they're not going to go as far because they're having to speed up. Okay, who's traveled farther? And again, the way you can do this is find the area. Okay, the area tells you how far they traveled. Polly would have traveled in 2 seconds at 1 meter per second for 2 seconds. She's gone 2 meters. Whereas Art, his average speed over those 2 seconds is half a meter per second. Okay, because he went from 0 to 1. So his average would be 0.5. And he did that average for 2 seconds. It's still area, it's just now area of a triangle. 1/2 base times height. We're doing his average velocity times his time. Half of this value times this. And that would give you 1. Okay, he would have only traveled 1 meter. At what point do they travel the same distance? This is a trickier question, but what you're looking for here is where they would have the same area. Okay, and that would be, I don't think I have any animations on there, I don't. That would be at 4 seconds, where the area of this triangle that's formed by Art, 4 times 2 divided by 2 is 4, would equal the area here, 4. Okay, so that's a trickier question. But that's how you know they have the same area there. Therefore, they have the same displacement. All right. I told you that you also have to be able to match graphs. So here's a position time graph, and here are 3 possible velocity time graphs, and I'm asking you which one matches this. I'm going to give you a moment to look at it. Okay, so I'm going to set a timer for 36 seconds. Please turn and talk to your neighbor and see if you can figure out which of these graphs, A, B, or C, matches the position time graph at the top of my screen. Okay, so take a minute to talk. Y'all think you know?
Yeah.
Okay. Our timer is about to go off anyway. It's for some reason not beeping, but okay. All right, which one do y'all think?
B.
B? Okay, so let's check. Okay, so B says the object moves forward at 2 meters per second. Okay, for the first part of this. So let's see. Is this 2 meters per second? After 1 second, 2 meters. After 2 seconds, 4. Okay, yeah, that looks good. Okay, then B says the object does what? What happens here? Stops. The velocity goes to 0. Okay, and this one does stop, so that looks good. Okay, then the object has to go backwards at, what is this, 1 meter per second? Yep. So let's see, backwards at 1, -1, perfect, and then stops again. Yes, B does look like it matches. Okay, you have to go segment by segment. Which way is it going? When does it stop? Like, make sure that it matches up. This does not have the same shape. It's not supposed to. Okay, some people want to pick things that have a similar shape, so you may have been tempted to pick C. Don't do it. Okay, it's this one here. It is B. So go piece by piece and match them up. All right, for the remainder of the class period today, you are working on the assignment 103.3 Speed and Velocity Problem Set. This assignment is due by 11:59 p.m. tonight. If you have already finished it, or if you finished it in class and are looking for some extra practice, I would recommend that you open up the unit summary in the Unit 1 folder. Remember, this is bonus points for your test if you choose to do it, but beyond that, it's a great review for your test or for the CFU that you have on Monday, okay? Because you do have a quiz basically on Monday that you don't get to have multiple tries on, okay? So if you want some extra practice prior to that assignment, then please, by all means, use the unit summary if you finish the assignment early. If you have questions as you're working, please turn and ask your neighbor. If you're doing math, have paper out so that you can work it out. Because if you ask me for help, the first thing I'm going to ask you for is to see your work if it's a math problem. Okay, or I may be asking you to draw a picture. So have out some paper. Again, if you're conversing with your neighbor, it's perfectly fine with me. That's okay. However, you have different numbers than they do. So please make sure that your conversations sound like, hey, can you show me how to do this one rather than what'd you put? Okay, because what you put is not going to help either of you. Again, if you have questions for me, please let me know. I'm going to go ahead and let you guys get to work. If you need a calculator, you're welcome to grab an Inspire from the side counter, or if you have your own, you can take that out.